Alrighty everyone, welcome back to our last day of COVID at home learning. I will be back on Wednesday. It will be a nice change. I hope this has gone well. I think we're going to be panther and tiger free today. One of them's pacing about right now. Okay, regardless, we are building up our way towards the uncertainty principle. We're going to do that almost entirely with spin up, spin down, Dirac notation, this and that. As always, let's review a bit of what we've covered. And I'm going to remind you of something I said a while ago. Recall that we last time talked about, we fleshed out basically all the different nuances of SX, SY, the operators, matrices, this, that. I realized a while ago I said something that may have been a little perplexing. I talked about diagonalizing and matrices. And let me review a little bit of that here, and that'll also allow me to write down all those matrices again, which is what I'm really trying to do. Okay, let's write down the SZ matrix. So there we go, that's SZ. And remember, the Pauli matrix is the same thing without the h bar over 2. Okay, now if I write down the Schrödinger equation, the eigenvalue equation, this is what it should look like. Remember, we use lambda for the eigenvalues of a matrix for some reason. We use a little omega for otherwise. Okay, so there we go. We talked a little bit about how we know that if this is, say, the plus state, the plus ket, then lambda would be h bar over 2, yada, yada, yada. Recall that the eigenvalue equation only works under the condition that the determinant of the operator matrix minus the eigenvalues times the identity matrix, which would result in this behavior. The diagonals get a minus lambda. That determinant has got to be equal to 0, or there's no solution. So we've done this last time. When you solve for lambda, you can see that you have hopefully you remember what a determinant is. This diagonal minus that diagonal, you're going to get a lambda squared. So of course that means that you're going to have two answers, and you should have two answers. You should have spin up and spin down. So anyway, just wanted to remind you of that. Now again, I wanted to review a bit what we talked about last time. So I'm going to do this, but I'm going to do it with SY. Okay, so let's look at the determinant of SY minus the identity matrix, and let's make that equal to 0. And this is going to allow us to figure out what the eigenvalues are of SY. Now we already know that those are also spin up, spin down, plus or minus h bar over 2. And if I solved SY in the SY basis, it's the same thing. It would be identical to this. So what I'm doing is I'm solving SY in the SZ basis. So that's just kind of horribly important. It's also good practice. Okay, so let's do that. So we're going to solve for this deal in the SZ basis. Okay, so I happen to know that SY is, of course, h bar over 2, 0 minus I 0. Okay, it's off diagonal, so that's going to make this more interesting. So therefore, this is, let's see here, h bar over 2. Okay, 0 minus the identity times lambda, so that's minus lambda. I h bar over 2, sorry, minus I h bar over 2, I h bar over 2, and then minus lambda again, because these diagonals are 0. So the determinant of this has got to equal 0. Okay, so let's see, what do I get? Oh, sorry, there's no h bar over 2. I've multiplied it through, my bad. Okay, diagonal minus diagonal, so that is lambda squared. Minus lambda. Okay, this is awesome. I've got minus. Now I get a minus because that's a determinant. Then I've got a minus I there. I've got an I there, so minus I squared. H squared over 4 is equal to 0. These are always fun. Minus I squared. What the heck? Just got to be careful. Okay, lambda squared I squared is minus 1, minus minus 1 is 1, minus 1 is minus 1. It sucks, doesn't it? Really confusing. Okay, and from here, I mean, we're done, right? So lambda is plus or minus h bar over 2. Okay, so look at that. We get the same eigenvalues, which we should have. So it's cool, everything works out. Let's see. Now, what I wanted to tell you a bit about was, I will often say, well, we got to diagonalize the Hamiltonian. Now, when I'm saying that, I'm talking about all of this. That means that is like an overarching statement for finding the eigenvalues, and then with eigenvalues, you figure out eigenvectors. To figure out eigenvectors, let's do that in this case. If you don't mind, let me do myself a favor and say h bar over 2 is 1, which it can be if we work with the proper units, where length is a Bohr, the mass of an electron is 1, time is in units of 10 to the minus 17 seconds, anyway, Okay, all right, now the way you solve this is, let's write down the SY matrix and the SZ basis, and we're going to multiply it by some coefficient, which represents, don't forget that this A is basically a multiplier for the S plus state. This B is like the multiplier. It's B, the minus ket, A plus ket, A, B minus ket. Okay, equals to the eigenvalue. Let's do lambda equals 1, so it's just equal to AB. Okay, and now really the eigenvalue is h bar over 2, but I'm going to make that equal to 1. Okay, it's not too hard to see. Let's see. 0 times A minus IB has got to equal to A. Now that's kind of weird, isn't it? But let's just write it down and see where we go from there. Okay, then I've got, okay, minus, did I put minus? Minus, that's plus, sorry. IA plus 0 times B is equal to B. So IA is equal to B. Okay, now what does this do, right? Okay, so figuring out eigenvectors is a little bit of an art form. Let's set A is equal to 1, and therefore, no matter which one of these you look at, B is equal to I. Let's see here. Is that right? So if that is the case, then SY plus is plus, because it's at A equals to 1, plus I minus. Okay. There you go, and that's the right answer. Give yourself some room, and likewise, if we solved this for SY minus, we would have found there we go. Sorry, I had to think about it for a second. But we would have gotten this result as well had we solved for lambda equals minus 1. Okay, now when I say, so now we've got the eigenvalues and eigenvectors. Now when I say that we're diagonalizing the operator, what that means is that what I'm going to do is I'm going to re-represent the SY operator in, oops, I didn't do that right. Bras on the left, kets on the right. So I'm creating a matrix here. Okay, so here's the matrix, and without working through it, it's going to be this. Let me bring back h bar over 2. Let's pretend I never got rid of it. There you go. So this is the SY operator in the SY basis set. So it's diagonal, and it should be because the eigenkets of the SY operator are SY plus and SY minus. It's identical to SZ, but of course, why wouldn't it be? Because SZ is defined to be its own, the S plus and minus are the basis kets of the SZ operator. So if I just say Y is Z, then I get the exact same thing. That's essentially what I've done. Anyway, and that's what it means to diagonalize a matrix. Now, in the matrix, of course, is the Hamiltonian, and the basis sets are atomic orbital. Kitty! Sorry, I've been having issues ever since Zoe came back from the vet. Okay, again, so if the matrix is the Hamiltonian and the basis sets are atomic orbitals, then the eigenvalue would be like the ground state energy. Of course, you can also get excited state energies, and the vectors would be molecular orbitals. So there you go. So that's why that's important. Okay, so anyway, that's what I was going to do in terms of review. I just mostly wanted you to look at those matrices again, and God knows you got tons of homeworks with them. Okay, now what? What are we here to really do? We're here to do the uncertainty principle. Uncertainty principle. I have to remember principle versus principal. Stop it, kiddies. I told him not to do this. Sorry about that. Okay, so the uncertainty principle is all about commutators and commutator. Stop that. Stop. Sorry. Maybe I'll edit that out. I don't know why they do this. Ever since Zoe got her tooth out, they've been fighting, and I think that's because there's been a shakeup of dominance. Stop. I think they had a shakeup of dominance, and that's not good for cat society. Zoe lost a tooth, so she's not alpha anymore. Anyway, all right. So, okay, that's a commutator. Recall an anti-commutator. We've already covered this. Is this? Two things. Anyway, there you go. Anti-commutator is when you add them together, which seems silly. You're not going to really see anti-commutators except this. What we're doing is we're going to prove the uncertainty principle, and this is the only time you're ever going to really see an anti-commutator. All right, when it comes to commutators, I do want to point out that they're equal to, if you permute the interior, you get minus itself. That's just odd. A minus B is minus B minus A, right? So that's kind of easy. Okay, recall that we also proved that for the spin operators that you get this deal, and you're doing some little homeworks with that. Again, it's really not particularly hard. The anti-commutators of the same is just h bar squared over 2, or is that h bar squared over 4? No, it's over 2, and the Kronecker delta. So there's not much to it. Okay. All right, still reviewing. But now what the uncertainty principle states is that for Hermitian operators A and B, and of course when I put a little hat that means operator, if the commutator is 0, they are compatible. And incompatible if the commutator is not 0. Okay. Now, so what does that mean? Let's see here. Okay, big picture. Let me tell you what the answer is, and then I'll prove it. Hopefully it'll kind of guide you a little bit. What I'm going to prove is that the basis of A. Let's see here. Let me just write down the eigenvalue equation in ket form. Okay, so this means that A and A dash, A double dash, A triple dash, A1, A2, A3, again, book notation's a little funky. All of those are eigenkets of the operator A. Now, what it means for A and B to be compatible is that these kets are also eigenkets of the B operator. That's what that means. Now, what I want to prove is, the way I'm going to do that is to prove that B is diagonal in the A basis. So we just talked a lot about how like the SZ operator is diagonal. Remember that diagonal, A is diagonal. So the way you represent that is, 0, 0. Sorry, that's a 0. So the A representation of A in its own basis set is a diagonal matrix, right? And you've already seen that with SZ. And let's see, now what we're going to prove that B is diagonal. Okay, so if B is diagonal too, that means that these set, this complete set of A states, is also the eigenkets of the B state. So when you represent the B matrix using the A basis set, if it's diagonal, then they're eigenstates of both operators simultaneously, and that's what that means to be compatible. Okay, now, and also, so in contrast to incompatible, take Sx and Sz. Those do not commute. The commutator is not zero. So if you operate, if you recall, you may recall this. I'm kind of jumping ahead. You do not get this behavior for the plus state, which is the Sz basis ket. If you operate on Sx, you do not get an eigenvalue times the plus state. In fact, I think what you actually get something times the minus state. So the states plus and minus, the kets plus and minus, are not eigenkets of Sx, and that's because their commutator is not zero. Anyway, I'm kind of jumping ahead, so I hope you didn't write that down or anything. That may be kind of confusing. Okay, now I'm trying to prove that B is diagonal in the A basis, and let's see, how do I do that? Okay, so what I'm going to do is, all right, for one, if that's the case, I need to change how I designate these states. I need to start doing that. Otherwise, it's confusing, and that's because I've got another operator, and it's going to return its own eigenvalue. So the B operator is not going to return the A eigenvalue, because that makes the B operator the A operator. The point is that they're not the same operator. I mean, why would I be talking about that, right? That doesn't make any sense. It's going to return its own eigenvalue, which is distinct from A, but the states themselves are the same. Okay, so here's the proof. Now, another thing to note is that for the uncertainty principle, we're always working with Hermitian operators. And that's because Hermitian operators are operators of things that are real, like momentum and energy. Uncertainty, I don't need to work with anything other than observables, because the uncertainty principle, the purpose of this is talk about your measurements. There are operators that are not Hermitian, and they do not correspond to observables. Non-Hermitian operators, they do things like turn a ground state to an excited state, just because that's kind of cool. There's reasons to do stuff like that, but that's not an observable. So observables like momentum, position, energy are all Hermitian, and those are the only things that are going to be applicable to the uncertainty principle. So I'm always doing these with Hermitian operators. And so recall that means that, A this is actually important here in a second. So that's Hermitian. I actually need that in the proof. Okay, so the proof. Okay, the trick is, now remember I was saying that I was talking about commutators, so I'm going to write down a commutator, and I'm going to bracket that with like the ground state and first excited state of whatever A is. And if you look at this and you're like, well, what do I do from there? Well, the smartest thing would be to expand the commutator, because by itself it's just like a symbol, right? But the symbol has meaning. Right, you just permute, subtract the permutation. Okay, so there you go. Next bit, you're thinking like, what do I do there? Remember that this is just like middle school algebra. So now what you're going to do is you're going to bring over a double prime. Okay, this looks the same. Okay, bring this guy over here. You see that? A prime. See? All right, not too bad. Oops. Almost write A, I should wrote a B. There we go. Saved myself at the last moment there. Okay. Now I see I have A operating on the A ket. Now, so I know that I can do this. A prime is a number, and the A ket is still just the A ket. So that's just a number, so it can come out front. And so what I'm left with is this. A double prime B, A prime, oops, I forgot my little symbol there. There we go. Okay. So, right, hopefully, this is stupid easy. Okay. But now I got a bit of a problem here. Now, you can't, you may be thinking like, oh, well, there's a bra, there's the A operator, there's an A bra, so just operate. No, remember that the dual, to be dual, you have to have this. You have to have that, right? You can't operate on a bra with an operator. You have to operate on the adjoint of the operator. Oh, wait a minute. A is Hermitian. So I can do this. I can just write this down. Now note that in that case now I've got a double prime, the eigenvalue, technically the complex conjugate, but guess what? The eigenvalues of Hermitian operators are real. So now A is gone, so I've got a double prime the ket, B operator. I don't know why I'm writing so small. Okay, and now what I've got is, now I can finish this A double prime minus A prime. And I don't know if you noticed, but these, oops, little hat, it needs a little hat there. And don't forget that all of this has been equal to 0 the whole time. Commutators are equal to 0. Okay. Now the thing is that this factor, remember this is like, let's say A is the Hamiltonian, then these are the energies, and this would be the ground state energy, and that'd be excited state energy. That's not 0. So that's 0. So A double prime B, A prime is 0, and these are off diagonal matrix elements. Sorry, my handwriting's kind of bad today. Those are off diagonal matrix elements. Okay, so therefore B is diagonal. Therefore, if I represent B as an operator, what you get is B prime, B double prime, B triple prime, 0, 0. And that's in the A basis, which is really the AB basis, like I mentioned before. Okay, so again, if the commutator of two operators is 0, then they have the same basis states. Each can return a distinct eigenvalue, but the states are still the same. Okay. Now, that's all fine and good, but the crux of the problem is when the commutator is not 0. Okay, so so we're still talking about the uncertainty principle, and now we need to define a variance, also called a dispersion. Now, one thing is that due to the mathematical complexity of quantum, the fact that it's a statistical mathematics often gets lost, but this is pure statistics, and it's funny how often that gets obscured. When it comes to statistics, a variance is literally the most important thing, right? A variance is variance, right? Okay, a variance is this. It'll be the change of an operator. Well, here, let me write down the change of an operator. You may guess that I'm gonna square it here in a second. Okay, you know all right. So the measurement minus the average. Now the problem with this is that if I was to take the average of this is just a number. So what I'm going to end up with is the average minus itself. So that's 0. So that's kind of useless, right? So it's almost guaranteed that this by itself is 0. An average minus an average is 0. In fact, it's guaranteed to be 0. Okay, but when you square it, you aren't necessarily going to get 0. And by the way, this is a variance. A standard deviation, which are also known as error bars on graphs, is the square root of a variance, right? So, all right, now let's figure out what this is. All right, so this is equal to, let's do an average. Let's do the average. Okay. First, I'm going to figure out the operator. Okay, operator squared minus 2 operator average value. Now, the reason I can do that is that, remember, the average value is a number plus the average value squared. Now I got to take the average value of that, and just like we were doing before, I mean, these are kets. That's a bra, that's a ket. And I'm not even going to make it look bra or ket-like because it's kind of silly, right? because it's just like an alpha or an A or whatever. Minus 2 A squared. So this that's 2. That's the average of A. That's already the average of A. Okay, so you can see those basically cancel. You end up with the average of A squared minus the square of the average. The average of the square minus the square of the average, right? And that's what a variance is. And a standard deviation is equal to the square root of the variance. Okay, that's just statistics 101. Okay, so what about that? Now it turns out that when you're talking about an operator and you're examining it with its own basis, you're always going to get 0. So let's do a little practice. Let's see. Now another thing I got to mention that you have to, when we're talking about these kinds of analyses, variance, standard deviations, you have to be specific. You can't do these types of calculations in general. You have to talk about these calculations. What's the variance? What's the this or that for specific states? Okay. So what I'm going to do is, what is SZ squared for the plus state? Right now, again, I can't say what is this in general. I need to apply. I need to apply a state. Now, it may be true that it doesn't matter whether I apply plus or minus. That could come out to be true, but that would be actually more pure luck. Okay, now to do this, let's see. If I do this with a matrix, that would be great. But you know what? I'm going to do this. I'm going to do this the hard way. So that is going to be h bar squared over 4, and I've got plus minus minus minus. Plus, I took both have h bar over 2, so that's h bar squared over square plus minus minus minus. Okay, so what do I get? H bar squared over 4. Nothing changes. Oh, wait a minute. No, look at that. I'm going to get plus, minus, minus. Oh, that's kind of interesting. Okay, so therefore, when I do this, if I do plus, plus on either side, what you get is just h bar squared over 4. Okay. Okay, now I got to subtract from that. I got to figure out what SZ is. And then square it, and that's not too hard. Let's see here, that would be plus h bar over 2 plus, by definition, here's the operator, plus minus 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 plus. Okay, so only so it's just h bar over 2. Okay, square everything. Okay, sorry, I put a minus sign in front, and that's why SZ squared minus SZ. Oh, hello. Oh, we got a little visitor here. I don't know if there's. I see you, kitty cat. Okay, this is 0. Right, okay. So, oh, you can't see that, sorry. H bar squared over 4. No, Zoe. No, I know. No, cat. Sorry about It's always exciting around here. Well, it makes it a little bit more fun, huh? She hasn't ever really shown much interest in this, and all of a sudden now she's interested. Anyway, okay. So anyway, that's just a little bit of practice, and again, one of the little rules about all this jazz is that the uncertainty in a state, that is, the uncertainty of an operator as evaluated from its own eigenstate, there's no uncertainty because that's what it means to be an eigenstate of an operator. Of course, it gets more interesting when you why are you even talking about that? By definition, you know exactly what's going on. It's what happens when you want to look at the SZ state, but project it on, when you're working in the SX, when you're asking SX questions. Okay, so in general, and we're going to prove this, in general, the uncertainty principle states the following, that delta A for an operator, again, you have to square these, otherwise they're zero, is greater than equal to 1/4. You'll see where that 1/4 comes from, the commutator. Okay, commutator squared. Okay, now remember that the commutator is its own operator, so what you do is you'd write out these operators, and then again, you always have to define, I know I'm being generic here with this little a bra and a ket, but you do have to decide on a state, whether it's plus or minus or any of the other zillion things we're going to be looking at. No, Zoe. There's nothing up there, okay, kitty. So I'm using a step ladder, and so she's decided she has to climb up the step ladder. Okay, now one example, I just want to point out that hopefully you know this one, and of course this is x minus I h bar d dx minus, so it'd be plus I h bar d dx x. And the way you would figure this out, so what is that? You take a wave function and then divide by the wave function. This is an undergrad level thing. I hope you've seen this before. And what you'd find is that the result is I h bar. And therefore, the dispersion in X, dispersion in P, sorry, my handwriting is bad today, would be h bar squared over 4. Sorry, greater than equal to h bar squared over 4. Anyway, that's one thing. We're going to cover this again. I just wanted to remind you that at an undergrad level, I'm hoping you've all seen this before. And if not, this isn't exactly hard to work through. You should have seen this before. I just wanted to point that out. And I'm also going to give you a little handout probably on Wednesday, and we're going to revisit this. There's an interesting problem that I want you to think about. It's not a homework assignment, but it's an interesting problem. I'm gonna remind you about this. I'm gonna show you an interesting problem, which is gonna make total sense, and then I'm gonna give you a spin problem that isn't gonna make sense. And I want to see if you can figure it out by next week. Anyway, so it's just a little bit of reminding you what this stuff looks like, and also I'm gonna set you up on a challenge problem. It's actually really a fun question. It's gonna kind of make you angry a little bit. Trust me, I need to shut up and move on. Okay, so let's prove it. Let's prove this thing right here. How do you prove it? Okay, first thing is you're going to use the Schwartz inequality. Now the Schwartz inequality is basically this. You know that for two dot products, remember how I often call eigenkets eigenvectors. Okay, so the dot product of two vectors is equal to the absolute value of those vectors times cosine of the angle between. So if you get rid of that cosine can at most be 1. It's usually less than 1. Therefore, the absolute magnitude of the vectors is always got to be equal to or greater. Equal to if cos is 1, if A and B are in the same direction, and if not, then it has to be, cosine has to be less than 1. So if you get rid of it, then the magnitude of A and B is greater than the dot product. Okay, so let's just remind ourselves of that. Okay, now in terms of applying this to bras and kets and Dirac notation, it looks like this. Okay, alpha, beta, dot products, inner products, what's wrong with me? Greater than equal to alpha, beta, but to make it, you've got two things multiplied, but that's one thing multiplied, so that doesn't make sense. So what you do is you take the absolute value square. So there you go. All right, so there's this. Okay, now to make headway, we're going to do something kind of funky. Okay, so here's step one. What we're going to do is we're going to do an inner product. We're going to recreate this. We're going to recreate this the following way. Let's start. We have to do a bra first. Bra's on the left. And I'm going to have some nebulous factor, lambda. Okay, here's the ket. And lambda is some weighing factor. Then I'm going to give it a value later on. It's also very closely related to one of your homeworks. Okay, now let me point out that this is an inner product, right? In inner products, based on what we covered, remember when we first started covering any of this stuff, an inner product is always greater than or equal to 0. It has to be, right? So, and remember, that's like by definition. Okay, now when you work through this, what you get is alpha plus lambda. Lambda is a number, so it can be manipulated quite readily. So that's this one. Then I've got lambda beta alpha. And then I've got lambda squared beta beta. Okay. Now you define. Now this is going to seem kind of out of nowhere, but I mean we can make this whatever we want. It's just a number. And so, and of course there's a trick here. The trick is to give it just the right definition. And magically all this works. So again, I'm always saying that I think these people knew how to do these proofs because they knew the answer and they were able to reverse engineer everything. Okay, with that, now what do you get? You end up with, okay, alpha alpha. Okay, I'm just writing down lambda. And then alpha beta divided by beta beta. You can see why there's a beta beta. It's because of that last term. Okay, anyway. Okay, minus, I'm writing lambda again, beta alpha. Beta alpha divided by beta beta. Okay, then, okay, so then you're going to get lambda squared. Okay, lambda squared is going to be beta alpha. Okay, now I've got a beta beta. Okay, I got a beta beta divided by beta beta squared. So that's just beta beta. Okay, so I've done a little algebraic step there. Hopefully it didn't blow your head off. And look what I got. You see, now that's the trick. That's why we make lambda. That, like, why the heck did we pick that? We picked that so that this would cancel. And notice that this is the complex conjugate of that, and so therefore alpha alpha minus absolute value of alpha beta squared. Right, a number times its complex conjugate is the absolute value over beta beta. It's greater than or equal to 0, and therefore, actually, I guess I should have mentioned to you what I was doing as I was proving this. I probably wasn't clear on that, was I? So I bring this over and bring over beta beta. That's greater than or equal to alpha beta. Sorry about that. Yeah, I should have mentioned. When I wrote this down, it probably was like, oh, yeah, oh, okay, where does that come from? And I didn't mention that's what I was trying to prove, so I screwed that up. Anyway, okay, so there you go. Okay, now the next thing to do is, so this is all step 1. Step 2. It's going to seem kind of very hand wavy at times. It's like I'm making up things because it's convenient. I'm not. Trust me, I'm not. But anyway. If A and B, but A are Hermitian And remember, we're not interested in non-Hermitian operators. Non-Hermitian operators don't correspond to observables. Why would I care about the uncertainty principle about something that's not observable? What that means is that alpha is equal to its own complex conjugate, and therefore the expectation, remember this is an expectation value. The expectation values, remember that this is the expectation value, the eigenvalue. It becomes an expectation value when it's calculated this way. Everything is real. Okay, so that's kind of important. Okay, now here's another neat thing, and this is part on your homework. I think homework 5, by the way. Okay, if B is equal... Okay, so this is Hermitian, but if this is true, then the expectation values are imaginary. Purely imaginary. Okay. Now, hint, the reason we're doing this is A plus IB, the absolute value is A squared plus B squared. So hint, this is why I'm doing this. You're going to see, because this is going to come up in a minute. All right. Okay, now what we're going to do is we're going to apply the, we're going to solve this starting with here. Alpha, alpha, beta, beta, and I'm going to make a substitution. And again, I told you that at times this is going to seem a little hand-wavy. This is the part that's going to seem a little hand-wavy. But it's not. It's not. I want to point out that for any operator acting on something, it's still a ket, right? The result is still a ket. Right? We've gone over that many times, right? And so that's why this is always an inner product. Doesn't matter what the operator is. Okay. So basically, operators don't really do that much. Now, the reason I'm bringing that up is, let's make alpha, let's define it as the action of the delta A, operator A minus its average, times some whatever, times some other state. It just doesn't matter, right? I mean, these are all just Greek letters anyway. Okay, and then of course, then on the bra side, sorry everyone, the spam calls, just constant spam calls lately. Okay, what we do is we're going to define the bra as some state. Delta A. There we go. Okay. Oh, that looks miserable. Sorry, it bothers me. Okay, delta A plus. Okay, so there you go. So so this is I don't know what state being operated on by the delta A operator. It's a function of an operator, right? But it's still, the result is still a ket. We'll call that alpha. And the same for the bra. I'm trying to be careful, so that I need a little, I need to say it's adjoint, right? Although A is Hermitian, so actually I really don't need to do that, but I'm going to write that down just to be careful. Okay, now the point of all this jazz is, let's go back here. Okay, now what I've got is, I've got whatever on the left, I've got A adjoint, and then on the right I got another delta A, so what I end up with is delta A squared, right? And then of course we'll do the same for B. Delta B squared, and these need little hats. Okay, and therefore we have to do the same thing right here. Delta A, delta B, they get little hats. Okay, so basically what you can do is, so you can either look at these formal definitions I gave, which is totally fine, or basically you can just take these expressions and insert operators in between them, and those operators being delta A, delta B, and that's totally fine too. Either way it works and it's perfectly legit. Okay, Now here's the magic. I'm going to go on a little aside here. Okay, delta A, delta B is equal to, so notice that we don't have a commutator. Here's where you get the commutator. Delta A, delta B. And remember, I also told you that you never see anti-commutators. Anti-commutators don't come up too much except in the proof of the uncertainty principle, which is what we're doing, and there it is. Okay, so now you see how we're going to make headway. In this side, so you see half of the uncertainty principle here, and we've got it equal to this thing via the Schwartz inequality. Now remember that we need to be inserting a commutator in here, and now we've made some headway. Now we're basically going to be just trying to get rid of that. Okay, so now what? The damnedest thing is, this is a little counterintuitive. A, B is anti-Hermitian. And that is because, let's take AB and let's look at the adjoint, and that is equal to AB minus BA, adjoint little hats. And in a homework, on homework 4, you're going to prove the following. So I'm going to just write it down because you're going to prove it. You're going to prove it with a resolution of the identity, if I'm not mistaken. Little hats, everything needs a hat. There we go. Okay, and then this is equal to, now again, Hermitian, right? The operators themselves are Hermitian. The commutator is anti-Hermitian. Okay, so there you go, and this is equal to minus AB. Okay, yeah, you can see that. All right, so what does that mean? That means that, therefore, delta A, delta B, I'm working, I'm basically, yeah, I'm still working here. So I'm taking this and I'm going to do the average value, is 1/2. Let's do the average value of delta A, delta B, plus 1/2 average value of the anti-commutator, delta A, delta B. They should have little hats, everything needs a hat. Okay. Now, if this is true, we've already talked about this, if the commutator is anti-Hermitian, then this is pure imaginary, and likewise this is pure real. Pure imaginary and pure real. All right, everyone. Sorry, I had a little bit of a flub. Just started writing down a bunch of stuff that wasn't right. So let me just start over real quick where we were at before. Okay, we were just talking about how you can represent these two standard deviations technically as a sum of a commutator and an anti-commutator. Now I just talked about how anti-commutators are pure real. It's not hard to prove that. Anti-commutators have pure real expectation values, and commutators are equal to minus their adjoint, so those make them anti-Hermitian. Commutators are anti-Hermitian, and therefore they are pure imaginary. Remember, we're doing the expectation value of these, and so these are actual numbers. Okay, all right, so there's this. Now let me, before you see where I'm going with that, let me point out where we were at a minute ago. Sorry that I don't have a continuous piece of paper here, but we were talking about the variance in A times the variance in B, these being operators. The Schwartz inequality gives us this. Okay. Now, what you can see here is that we're going to insert this into here. Now, this is where it gets kind of interesting. Okay, if I got this, now I got to square it, and that's this. So now I got to square that. So I got 1/4 absolute value of the delta A, delta B. Well, little hats. I keep forgetting the little hats. Okay, I've got this term squared. Then I've got the next term squared, the anti-commutator. Okay, then I've got what? Then I've got the cross term, right? Actually, no. This is why I made such a big deal out of pure real, pure imaginary. Recall that I just said this a minute ago, that when you have a complex number, a pure real plus a pure imaginary, the absolute value is this, right? So we're actually done. We're done here. You notice that, and you may think, oh, that's the uncertainty principle. Not quite. We're almost there. Oh, did I forget? Oh my God, I forgot to put that. I'm just kind of all over the place. Okay, so this is true. There's no cross term for the reasons I just mentioned, because this is pure real and pure imaginary. Okay, we're just 2 steps away from the uncertainty principle, and this is where this is kind of funky, but watch this. Just get rid of it. All right? So if this is greater than this and you get rid of a term, and since it can only be 0 or greater than 0 because of the square absolute value, then now this is like super true. All right, last bit. Notice that I've got the commutator of essentially the delta A, not A. So the last step in this process is to do this. Again, the variances multiplied of the 2 operators is greater than or equal to 1/4. Not the commutator of delta A, but the commutator of A and B. Okay. Now, notice that I just went from here to here. And why the heck did I do that? It turns out, and I want you to try this on your own. It turns out that that this is true. That the deltas just go away. Okay, and why? Okay, look at the definition of this. Or for one, just try it. And recall that this is what this is. Okay, it turns out that, remember, average value of A is already a number. And so what's going to happen is when you get delta A, delta B minus delta B, delta A, all those average values are going to cancel. So they're not there. And that means that the delta A just turns into A. Okay, so there you go. And recall that is the uncertainty principle. That's it. And so we've proved it. All right, so anyway, I think that's enough for today. We're going to go off in a very different direction on Wednesday. We're going to start talking about transformation of bases, like how do you go from SZ plus minus. You're going to use an operator to turn that into SX plus or minus. You're going to figure out how what's called a unitary operator is to change one basis set to another basis set. So that's very important because it is related to time dependence. And I've also, you are going to be revisiting all this uncertainty principle and actually on homework 5 when you're going to do this in a time dependent manner. And what we're doing is on the next lecture, we're going to start talking about transformations of basis using operators to do that, because that's how you're going to transform this uncertainty principle into a time-dependent form using operators that do that. So anyway, I've talked long enough. I hope this hasn't been too bad. I'm sorry for everything that happened. I couldn't help it. And I will see you all on Wednesday.